Hello, in this video we'll go through the mathematics in civil engineering. Our main focus will be vector geometry. Vector geometry uses fixed vectors to calculate the magnitude and direction of the forces which have a fixed position. It makes use of the x, y, z planes in 3D space. This allows for real-life problems to be visualized and solved. This is very useful in the design stage of construction, as the engineer is able to determine if the forces are appropriate for the design. Some of the applications of vector geometry are seen in the construction of bridges, such as the Danzig Bridge, the Ruski Bridge, Russia, which is the longest cable-stayed bridge in the world, front awnings or canopies, pulley systems such as this construction crane, and this radio tower. Next up we have Eden, who'll go through a mathematical example.
This is an example of how vector geometry could be used in a civil engineering problem. The diagram shows a cable-stayed bridge with 4 cables connecting point S at the top of the support tower to points A, B, C and D. Using the bottom of the support tower as the origin, each point can be given a coordinate in the 3D X, Y, Z planes as shown. From this, the vectors formed by the cables can then be calculated. In this example, it is assumed that each point has a 1.5 ton downward force acting on it. Multiplying this weight component onto the vector will provide the tension in each cable. To calculate the weight component for each cable, the 1.5 ton weight is divided by the vertical distance between point S and the points on the bridge, which in this example is equal for all cables. So for TA, it becomes 1.5 tons divided by 14. To calculate the tension in cable A, this weight component is then multiplied by the vector SA. Once TA has been calculated, the magnitude of the new vector can be determined by taking the square root of the x component squared plus the y component squared plus the z component squared. This then provides a tension force acting on the cable. For cable A, it is 1.87 tons. To calculate the tensions in the remaining cables, the process is the same, however substituting in the different vectors SB, SC and SD. Calculated out, the tensions in cable A and B are 1.87 tons each, and the tensions in cables C and D is 2.64 tons each. From this, the total tension force acting on point S can be determined by the summation of the tension forces in each cable. So T equals TA plus TB plus TC plus TD. Once added, the tension force acting on point S is given by the vector 6.43, 0, negative 6. For the tower on the bridge to be stable, there cannot be any forces in the X and Y directions. However, forces in the Z direction are acceptable. As you can see, at point S there is a force in the X direction, which means the tower could potentially fall. To compensate this, a cable must be added to the other side. To do this, we pick a point that will leave the system in equilibrium. In this example, that is the point P. To check that this will be adequate to cancel out the force in the X direction, the tension T calculated earlier is added to the tension in the cable P, so T plus TP, or T plus the weight component in P projected onto vector SP. Once calculated through, the resultant force vector on point S is 0, 0, negative 12. This is an acceptable result as the forces in the X and Y directions are 0, so the tower will not tip over. Therefore, this shows that the point P, negative 15, 0, 1, is an adequate connecting point for the compensating cable. Through this example, it is clear that vector geometry is an important part of civil engineering. Many civil engineering problems involving cables in tension utilize vector geometry when making calculations. This mathematics is important as it allows for the construction of cranes, pulley systems, and also road and footbridges that people around the world depend on.